in this lecture we will see how randomization helps in design of good data structures. Okay, so let us look at the problem that we are interested in solving today. So there is a universe U consisting of elements, let us say integers 1 to some m, and then there is a dynamic subset of U. Okay. And let us say that the size of that is roughly n. Okay, so it is varying, so it does not have a fixed size, but at any given time let us say it is very close to n. Now, we want to do certain operations on these data. The operations that we will be doing are insert an element, let us say x, into the set S to produce a new set, and then delete particular element y from the set, and then we will also have search or find. Okay, so if you are given a key, you want to know whether that element is present in S or not. So these are the operations that we want to implement, and we want to do this efficiently, and by which we mean we want to do all these operations in order log n. Okay, and we want, so this is our objective, and let us see how data structures and randomization can help us do these. So what we will do here is we will look at a new data structure called as Treap. Okay. So Treap is nothing but a marriage of binary search tree and priority queue. So let us understand what these components are. So Treap is nothing but binary search tree plus a priority queue or a heap. Okay, so let us understand what are these individual operations, I mean what are these individual data structures, and how we will do the insert, delete and find operations on them. Okay, so let us just take a sample data. Okay, so suppose this is our input data, so this is our S, and a binary search tree will be something like this. Okay, so if this is our input, then the binary search tree corresponding to that would be something like this. Okay. So the key property of binary search tree is that left subtree contains smaller elements than whatever is at the node, and right subtree contains larger elements. Okay. So suppose you have a partial subtree like this, and if you wanted to insert the element 10 into it, okay, so you check at the root. So 10 will essentially be on the left side of 12. Okay, so you will go here, and it is greater than 13, so it will go here, and it is smaller than 11, so you will go again to the left, and it is larger than that. So basically you will create a new node wherein 10 goes. Okay. So the insertion is easy, and if you wanted to delete, you can essentially unroll the process of insertion. So suppose you wanted to delete 11, it would mean that you can just connect 6 in the place of 11. Okay. If you had 2 nodes as children, you will have to do a slightly more complicated operation, but those can be done. So binary search tree is essentially a data structure where every node on the left subtree contains smaller elements and everything on the right contains larger elements than whatever is present at any particular node. So, this property should be true of every individual node. That is called as a binary search tree, and you can use this fact that insert, delete and search are all proportional. The time taken by these operations are proportional to the height of the tree. The second data structure that we would see is something called as a priority queue or a heap. Okay, so, in heap the key property is the heap property, which says value at the node is greater than values below it. Okay. So, if you look at the binary search tree, there are children which are which have larger value than the value of the node, but priority queue or heap that is not true. Okay. So, corresponding to this input, the one possible heap is as follows. The largest would of course be 35, and let us say okay, at the moment we will not bother about how these were constructed. Okay. So, if you look at this diagram on the left, that is a heap and this is a binary search tree. Okay. So, if you look at any node, for example, if you look at 22, you can note that its children are of value smaller than whatever is there at the node, and this is true not just for the node 22, it is true for every node in this particular tree, and such trees are called as heap. Okay. Given any input data, you can convert it into a heap in linear time, and the heap need not be unique. I mean, it is usually not unique. There could be, given the same data, you could make multiple heaps with that given data. The same is true for binary search tree, but if you are inserting in a particular way, then of course there will be a unique binary search tree. Okay. But for if you look at the data as just a collection or a set of numbers, there are multiple binary search trees and multiple heaps. Okay. So, now when we are given a collection of data, we are going to convert them, we are not going to store them as either binary search tree or as heap, but instead we will combine these two, and the combination essentially ensures that the operations that we wanted to do, namely the insert, delete and find, these can all be done in expected O log n. Okay. And the expectation is over some particular choices. Those choices are not really the input, but it is based on the coins, random coins that is flipped while the algorithm is run. Okay. So, let us now that we understand what are binary search tree and priority queues or heaps, we can define what are called as treaps. Okay. So, the input data is slightly different from the data for constructing a heap. While constructing a heap or a binary search tree, the input was a set of numbers. Here, while constructing treaps, the input is basically a set of pairs of numbers. Okay. So, let us say S is going to consist of numbers of the consist of pairs. So, A1 B1, A2 B2 and AN BN. Okay. So, on this particular set, we want to construct a treap. So, treap is nothing but a tree, okay, where the individual nodes are some AI BI. Okay. So, let us say AI1 BI1, AI2 BI2 and so on. Okay. So, the input data is kept in some particular way. okay, and there are going to be, this tree is going to consist of precisely n nodes, the input consists of n pairs, and we say that it is a treep if when restricted on the first coordinate. If you just look at the AIs, look at the diagram, look at the tree and erase all the BIs, you will get a tree with just AIs, with just the first coordinates. Restricted to first coordinate, the tree should be a heap, and restricted to the second coordinate, this should be a binary search tree. Okay, so that is a treep. A treep on input S is a binary tree such that restricted to the first coordinate, the binary tree T is a heap, and restricted to the second coordinate, T is a heap. A priori it is not even clear that given data we can organize it this way, but it is easy to see that given any set of pair of numbers, there is a unique treep corresponding to it. So, let us take an example. We are going to assume that the numbers, the pairs are all unique. Okay. The first coordinate we are going to refer it to as the priority, because priority is what is required in a heap, and the second coordinate is what we will call as the key. Okay. Now, we know that the topmost element is the element with the minimum priority. So, this should be 1 2. Okay, so, we are going to look at a min heap. So, 1 2 should be this element, and the elements on the left should be, on the left child should be everything which is smaller than 2 when you look at the keys, and there is no such element. So, there is nothing on the left. So, everything else is on the, everything is going to be on the right. Okay. And if you look at the remaining elements, the least priority is 2 8. So, that is going to be here. Okay. And on the left side will be all elements whose key value is less than 8, that is basically 3 7 and 22 3. Okay. And amongst them, the node, the root is going to be the one with the smallest priority. So, that is going to be 3 7, and as the other node is 22 3, and that will be the left child, because 3 is smaller than 7. So, 22 3 will be here, and all these other 3 elements will be on the right side of 2 8. So, 2 8 is already taken care of. So, there is 3 9 and 10 3, and out of them the least priority is 3 9. So, this node is going to be 3 9, and the only remaining node 10 11 is going to be the child of 3 9, and since 11 is greater than 9, this is going to be the right child. So, 10 11. So, this is a treep. So, if you just look at the first coordinates, it is going to be of this kind. Note that any node is smaller than its children, than any of its children, and therefore, this is a min heap. Whereas, if you look at the second coordinate, 2 followed by 8 followed by 7 followed by 3 and comma 11. If you look at any node, everything on its right is larger than that and everything on the left is smaller. Okay. So, this is a binary search tree. Okay. So, given any data, there is precisely one Treap corresponding to it. That is because if you assume that the keys and the priorities are distinct, the root node is going to be the node with least priority. Okay, and then the left child or the left subtree contains all nodes or all pairs which have smaller key value than root, and the right subtree contains all nodes which have larger key values than the root. Okay. And this subtree, there can be precisely one way that can be organized as a Treap, and same for the right subtree. So, once you make these subtrees or subtreeps, there is one way you can combine it, and that is going to give you a unique Treap. So, given any input data, there is precisely, I mean, if you assume that the priorities and the keys are all distinct, okay, the priority could be a completely different set from the keys, but as long as those sets are themselves unique, I mean, there is no repetitions amongst the keys or amongst the priorities, there is only one Treap corresponding to it. Okay. Now, we could do all the insert operations or delete operations or the find operations based on the values of the key. Okay. So, here what we really want to, the problem that we really want to solve is we have some particular collection of numbers. Okay. What we will do is we will convert each of those numbers into a pair. Okay. The second coordinate will be the number and the first coordinate will be the priority, and this priority is where we will introduce the randomness. So, what we will do is, given any collection of numbers, we will choose a priority, a random number between 0 and 1 chosen uniformly at random, and that will be the priority of this particular number. Okay. So, you can say that since we are choosing it uniformly at random between 0 and 1, with probability 1, every number will get a unique priority. Okay. So, if the keys were themselves distinct, the random choice also is not going to introduce any identical priority elements. Okay. So, given a collection of input, we are going to choose a random number between 0 and 1 as the priority for that, and then generate the heap corresponding to it. Okay. Once we generate the sorry, not the heap, but the Treap corresponding to it. Once you have the Treap corresponding to it, we want to see if the insert operations and delete operations can be done quickly, can be done in order log n, and whether the search operations can be done in log n. We will see that all these operations, the time taken to do this depends on the height of the Treap. The Treap is a tall Treap, then it is going to take long time. If it is short, it is going to be the operations are going to be fast. What we will argue is that because of our randomization, the Treap's height is going to be bounded by log n in an expected sense. Okay. So, in a nutshell, what we will do is convert input sequence, which was a sequence of integers, into a sequence of pairs. Okay. So, if the input, if you think of them as keys, we will convert it into priority key pair, okay, and then we will construct the unique treap. Okay, if you are introducing a new element, that will also result in a unique treap which can be incrementally computed from the existing treap, okay, and then we will argue that because of randomization the treap height is bounded by O log n. Okay. Okay. Now, when we are inserting and deleting, we haven't yet argued that the insertions can be done in time proportional to the height of the tree. So, let us first look that. For that, there is an important notion called as rotation. So, let us say that this is a particular tree and where there is a value and there is a key and a priority. This is the priority and this is the key. Okay, so, let us say that we have some tree or treap at some point of time. So, this is a root node and it has children. Okay, so, let us say that one of the child was A, the child of the child was A, the other was B and the other was C. Okay. So, these are two nodes. Okay. We can convert this via rotations, we will call that as a left rotation and a right rotation. Okay. So, if you do the left rotation, you will get another tree. So, let us call this as D and E. Okay. Note that D and E are basically nodes and A, B, C are all they are themselves trees. Okay. If you right rotate, what happens is when we rotate, giving a rotation to the right side, what happens is E comes on top, D goes down, A comes up and D has two children now, C and B. Okay. And if you left rotate this, D comes up, E goes down and A goes further down and B attaches itself to E. Okay. So, this is an operation which is this left rotation and right rotation are well defined for binary search trees. Okay. In a priority queue also we can think about these operations, but they might destroy the priorities. Okay. We will see whether treaps we can do these kind of operations on treaps. Okay. So, let us say that if you rotate it in this kind, there were some existing values at these particular nodes, keys. Okay. So, key observation is that keys still satisfy BST property or the binary search tree property. Okay. Because everything in A should have been lesser than everything in E, which is clearly satisfied in both trees. In tree, I mean, if you look at this as call this as tree 1 and tree 2. In tree 1, if you look at node A was less than E and that is still valid. Okay. And every value in D, I mean, so we can look at it node by node. We will just do a couple of examples. If you look at node E, A consists of smaller elements and B consists of larger elements. Okay. That property is still true because A is in the left subtree, B is in the right subtree. Now, note that D is going to be greater than E and C is going to be greater than D. Okay. So, D is greater than E and C is greater than D. Okay. So, both D and C are greater than E and therefore, in the tree 2 you have both D and D and B is anyway greater. So, E is smaller than B. So, all those relationships are satisfied for E. So, you can do this for all possible combinations and you can verify that these are rotation operations, if you rotate to the right, it will basically preserve the BST properties, and if you rotate to the left also, the BST properties are maintained. Okay. Now, when we are inserting and deleting, we can use these operations to ensure that at no point we require more than the height. We can maintain the Treap property by ensuring, by doing these things properly. Okay, let's see that. If you had to just maintain the binary search tree property, we could just insert, and when you insert the binary, when you will insert it ensuring the binary search property, but the element that is inserted may destroy the Treap property. For example, in this particular data, if you think of S as the input data, and if you wanted to insert an element, so if you wanted to insert an element 4, 9, okay. So here is an element whose key value is 4 and priority is 9, okay. If you try to insert based on 4, what happens is, we are just looking at the key value, it is greater than 2, so it should be on the left subtree, on the right subtree, it is less than 8, so it should be on the left, it is less than 7, it should be on the left, and 4 is greater than 3, so it should be on the right. So this is going to be 4, this its priority was 9. Okay. For this node, the Treap property is not valid, okay, because here is a node whose priority is 9 and that is below a node whose priority is 22. So the priority has to be adjusted. Okay. So what we can do is, we can rotate accordingly, we can do these operations, rotations, left rotations and right rotations. Okay. These operations do not kill the BST property, but we can use this to adjust the priorities. Let us see how that is done. Okay. So from here we could move, you could do a left rotate, and therefore 9 4 goes up, so 9 4 goes up, and 22 3 comes down. Okay. Now this ensures that the BST property is maintained at this particular node. Okay. Between these pair of nodes, the BST property and the tree property is valid. But now if you look at let us say 3794, okay. So here every node, its BST property as well as the tree property is holding, because 2 and greater priority and greater priority and greater priority. So maybe if this node had a higher value, you might have to do a right rotate. Okay. So basically by a sequence of left and right rotations, you can ensure that the tree property is maintained. Okay. So in a nutshell, what we have argued is the following: insert based on BST property. When you do this, the time taken will be proportional to the height. Now, once you have inserted a particular pair, the tree property need not be maintained. So we will do appropriate right and left rotations to ensure Treap property. Tree property, in the sense, the BST property comes for free because we had inserted based on the BST property. The rotations either in the left side or the right side do not affect the BST property, but we are using those to adjust the priorities. So by doing a sequence of left and right rotations, we can ensure that the tree property is also maintained. Okay. So suppose you had some particular node like this. Okay, so let us say this was your temporary trip, and then we wanted to insert an element. The BST property ensures that the element was added here. Okay. Maybe this node it had to go somewhere else, so that the tree property is maintained. So, you look at these two nodes and decide whether it is to be rotated right or not. Okay. And then if it is rotated right, what happens is this node becomes the newly added node goes up. Okay. And then maybe depending upon these nodes you might have to rotate it left or right. Okay. And maybe this goes up. So, the total number of operations that happen is going to be bounded by the current height of the tree. Okay. So, this operation also in this the time taken is proportional to the height. Okay. So, what this means is any insertion in the tree can be done in time proportional to the height of the tree, and deletion is exactly same as insertions. Just delete an element, and if it is an intermediate element you might have to readjust so that the tree property is maintained. So, all those operations it is similar to the usual binary search tree operations with these rotations, okay, and they take time proportional to the height of your tree. What we need to argue is that the height of the tree in the expected sense remains small, in the sense it is going to be equal to O log n. Okay, so, that is what we will show next. So, this is our theorem. The expected height of a tree with n elements. So, let us say we have done a sequence of insertions and deletions, and finally, we have n elements, okay, and the expected height of the tree with n elements is O log n, and therefore, all these operations insert, delete, search etc., can be done in O log n expected time. Okay. So, how do we prove such a statement? Okay, this is happening because of the random choices that we have made. The priority q that was there with respect to the first coordinate, that priority q, its height is never going to be more than O log n in an expected sense, okay, and that is what helps us to maintain the overall height. So, let us introduce some notations. So, xi will denote the ith smallest node, okay. In terms of when you say ith smallest, this is in terms of the priority, okay. So, this ith smallest node in terms of the priority, not on terms of the key value, will be somewhere in the tree. We will look at its expected height, okay. So, let us denote it by a random variable. So, let us say capital Xi we will define as the height of the ith smallest node. This is a random quantity because it depends on when this element was added and so on, okay. We are assuming that each element gets a random priority, and that priority is being used to create a point pair, the first coordinate being the priority and the second point being the key, okay, and xi is the height. Let us introduce some more random variables. So, we are looking at the event that node j is an ancestor of ith node, okay. So, let us indicate this by the random variable iij. So, iij this is equal to 1 if ith node is an ancestor of j in the tree. Okay. And summation j going from 1 to n ij will denote the number of ancestors of I. We want to show that. So, if you denote this by the random variable, let us say yi, we want to show that expected value of yi is equal to O log n. The expected value of yi, it is approximately log n, it is bounded by log n, that is what we want to argue. This is sum of certain random variables. So, expectation of yi by linearity of expectation is the expectation of ij summation j going from 1 to n. Okay. So, now what we want to know is the expectations of these individual iij, but the expectation of an individual indicator random variable is nothing but the probability of the event that indicates. So, this is summation j going from 1 to n probability that ith node is an ancestor of jth, the node ith node or xi is an ancestor of the jth node. Okay. So, ith node here means that particular pair which had ith smallest priority, and jth node would means jth smallest priority. Okay. So, we have to slightly modify our argument. Here we were looking at the smallest in terms of priority, but let us look at, I mean, we could do this entire analysis on the basis of the key values as well. Okay, ith smallest node means the key value is ith smallest, and jth smallest means the key value is the jth smallest. Okay. Now, so these were our numbers. Okay. The keys were, let us say, from some particular set, the ith smallest key value, that node is what we call as xi, and the jth smallest key value, that is what we call as xj, and so on. So, probability that the ith smallest key value is an ancestor of the element with jth smallest key value, this is the probability that we need to ascertain. Okay. So, let us look at these elements I and j. Okay. So, small and we have lot of numbers in between as well. Okay. So, we will have a lemma which will help us estimate this probability. Okay. xi is an ancestor of xj if and only if I has or xi has least priority among all the elements whose key value is between xi and xj. So, we have these nodes xi and xj, okay, and all elements appearing between I and j, let us call that as the set S. Okay. So, S is a set of all elements, the key values is between I and j. Okay. What we want to prove is all elements in S has larger priority than xi. Okay. So, we will split the proof into 4 parts. Okay. We had a Treap and suppose xi was the root. Okay. By virtue of it being the root, its priority is going to be surely smaller than the priority of all the other elements. Okay. In particular, all the elements in S will have strictly smaller priority. Okay. So, if xi was a root, then we know that I is an ancestor of j and i's priority is smaller than all elements in S. Okay, so that is case 1. Now, if j is the root, it is the same argument, xj is the root, then we know that j is an ancestor of I, and therefore, by virtue of j being the root, its priority is the least, and therefore, its priority is smaller than all elements in S, is the smallest. Now, if it is not root, there are two cases. They could be in the same subtree or they could be in different subtrees. Okay. So, the third case, xi and xj in same subtree. Okay. So, that means there is some root and then xi and xj is in this subtree. Okay. By recursion, you can say that the same argument should work. Okay, because now you have a smaller set of numbers. Okay, these numbers, they are strictly smaller than that. Okay, and xi and xj are elements here. Okay, and if there is an ancestor descendant relationship between xi and xj, we can restrict our argument to the smaller subtree. If they were in different subtrees, what do we do? Okay, so that is our fourth case. Okay, so let us say the root node is some xk and this is a subtree containing xi, this is a subtree containing xj. Okay. Now, one of them is on left and the other is on right. The elements on the left, by nature of the BST, we know that, I mean, if xi is on the left, xi is less than xj. Okay. And in particular, your xk is going to be lying in between xi and xj. If you look at the key values, the key value of xi is going to be less than the key value of xk and the key value of xj is going to be greater. Okay. So, this would mean that I is less than k is less than j. Now, k is an element in between I and j and that has the least priority from the set S. Okay. xi is the node which is having least priority, okay. And therefore, if you look at the elements in between xi and xj, xi is not an ancestor of xj, xj is not an ancestor of xi, and we have neither of them, neither xi nor xj has the smallest priority, it is some other element, and therefore, that takes care of all the 4 cases. Okay. So, this means that whenever some element is an ancestor of some other element, that particular node has least priority. So, now all that we need to estimate is the probability that a particular node has least priority amongst a collection. Okay. So, that would help us calculate the expectation. Okay. We needed to compute this probability that the ith node is an ancestor of the jth node. So, this is equal to summation j going from 1 to n, probability that the priority of ith node is smaller than priority of jth node. Okay. So, if you take the case that I is less than, so this summation we can split it into 3 parts, summation j going from 1 to I minus 1, probability that the priority of the ith node is less than priority of jth node, plus summation j equals I plus 1 to n, probability that the priority of the ith node is smaller than jth node. Okay. And this is what we, because if you take the case where j equals I, that probability is 0, and this probability. Okay. So, here in this side we have some particular j, and amongst the set 1, so let us say this is 1 I and here is your j. So, you have I minus j elements. Okay. So, I minus j elements which are competing to have the least priority. The priorities were chosen randomly. So, every element has equal chance of being the lowest priority element. So, I being the least priority happens with probability 1 by I minus j. So, this summation plus summation j going from 1 to n, 1 by j minus I. Okay, when j is greater than I, this is going to be 1 by j minus I. So, these probabilities have to be summed. This is going from j going from 1 to I minus 1. Okay. So, each of these terms you can upper bound by the harmonic number. So, this is going to be less than 2 times Hn. Okay. And Hn is approximately log n. So, this is 2 log n. Okay. So, what this means is that the expected height of any particular node is bounded by O log n. Okay. And that completes the proof. And we will start a new topic on hashing in the next lecture.